There's a hidden hand shaping everything you see in the night sky, a force so vast, so mysterious, it defies our senses. Picture this: every galaxy, every swirling nebula, even the delicate dance of stars, all held together by something we can't see. Dark matter, cosmic filaments, gravitational tides, these are the invisible architects of the universe, the silent builders of reality itself. And yet, for all their power, they remain just beyond our grasp, like shadows flickering at the edge of understanding. What if I told you that without these unseen forces, the cosmos as we know it would unravel, that the very fabric of space and time depends on structures we're only beginning to comprehend? This isn't just a story about distant galaxies or abstract physics. It's about us, the atoms in your body, the ground beneath your feet. They are all part of a grand cosmic blueprint, one written in the language of invisible forces. Think about that for a moment. The same mysterious web that sculpts galaxies also connects you to the birth of the universe. It's a humbling thought, isn't it? That we're not just observers of the cosmos, but active participants in its unfolding drama. And yet, for centuries, we've been missing half the picture, blinded by the limits of our own perception. But today, that changes. We're about to pull back the curtain on the universe's best-kept secrets. From the ghostly tendrils of dark matter to the colossal highways of gas and dust that stretch across billions of light years, we'll explore how these hidden structures dictate the fate of everything. And here's the most thrilling part. Every discovery we make brings us closer to answering the ultimate questions. Where did we come from? What binds the universe together? And what does it all mean for our place in the grand scheme of things? So settle in, because by the end of this journey, you'll never look at the night sky the same way again. To understand the cosmic web, we have to rewind time back to when the universe was just a newborn, a seething ocean of energy and matter. In those first moments after the Big Bang, tiny fluctuations in density, no larger than quantum ripples, began to stretch and grow as space itself expanded. Over billions of years, gravity took hold of those faint wrinkles, pulling matter into vast, thread-like structures, the filaments of the cosmic web. Think of it like this: if you could see dark matter, the universe wouldn't look like a starry night. Instead, you'd see a shimmering spiderweb with galaxies clinging to its strands like dewdrops. But here's what's truly mind-bending: this web isn't static. It's alive with motion, a dynamic highway where galaxies slide along filaments like beads on a string, drawn toward massive intersections called galaxy clusters. These clusters, the web's busiest hubs, shine like cities in the cosmic dark, where thousands of galaxies crowd together, bound by gravity's unbreakable grip. And just like cities shape the flow of traffic on Earth, these clusters dictate the movement of matter across the universe. Yet for all its grandeur, the cosmic web is fragile. The same filaments that build galaxies can also tear them apart. When galaxies collide in these dense knots, they're often stripped of their gas, the raw material needed to birth new stars. It's a cosmic tug of war, creation and destruction, playing out on scales so vast they defy imagination. And the most astonishing part, we're only seeing a fraction of it. The web's true structure is mapped in dark matter, an invisible scaffold that telescopes can't detect directly. Instead, scientists piece it together like detectives, studying how light bends around unseen mass or tracking the motions of galaxies caught in its pull. What's even more remarkable is how this hidden architecture shapes our own cosmic neighborhood. The Milky Way isn't floating in isolation, it's part of a filament, drifting toward the immense gravitational pull of the Virgo cluster. One day, billions of years from now, our galaxy will merge with others, drawn into a bustling galactic metropolis. So when you look up at the night sky, remember, you're not just seeing stars. You're glimpsing the threads of a tapestry woven by invisible hands, a masterpiece still being crafted since the dawn of time. Dark matter works like the universe's silent scaffolding, an unseen framework that holds everything together while refusing to reveal itself. Imagine building a house where 85% of the structure is made of glass so perfectly clear, you can't even tell it's there. That's the paradox of dark matter. It doesn't glow like stars or obscure light like dust. It doesn't collide with atoms the way ordinary matter does. And yet, without it, galaxies would spin themselves apart, stars would scatter like beads from a broken necklace, and the cosmic web would unravel into chaos. How do we know it exists? The evidence is written in the motions of galaxies. Take our own Milky Way, its outer stars orbit so fast they should fling into the void. But something invisible, something with tremendous gravitational pull, holds them in place. Astronomers call this the missing mass problem, and dark matter is the leading solution. But here's where it gets even stranger. Dark matter isn't just sprinkled randomly through space. It forms vast, diffuse halos around galaxies, and its gravitational fingerprints sculpt the universe on the largest scales. When light from distant galaxies bends around unseen mass, like a straw seeming to curve in a glass of water, that's dark matter warping space-time itself. Scientists have spent decades chasing this ghost. Underground labs shield detectors from cosmic rays, hoping to catch a fleeting interaction with a hypothetical dark matter particle. Particle colliders smash atoms at nearly the speed of light, searching for traces of something new. Even space telescopes map the invisible by studying how its gravity distorts the light of millions of galaxies. Yet so far, dark matter remains stubbornly hidden. Some theories suggest it's made of weakly interacting massive particles, while others point to actions, ultra-light particles streaming through space like an intangible breeze. There are even bolder ideas like modified gravity, suggesting Einstein's equations might need rethinking. But here's what's undeniable: dark matter's influence is everywhere. When two galaxy clusters collide, their visible gas smashes together and heats up, glowing in X-rays. But telescopes reveal most of the mass isn't in that gas. It's in an invisible component that sailed right through the collision, unfazed. That's dark matter acting like a cosmic ghost, passing through itself and everything else without a trace. And this isn't just some distant phenomenon. Right now, rivers of dark matter may be flowing through you, through the room around you, without a single atom in your body noticing. It's a humbling reminder that the universe is far stranger than it appears. Every time we think we've grasped the rules, dark matter whispers, there's more to the story. So while we haven't unmasked it yet, each failed experiment, each unexpected observation, brings us closer to rewriting physics and understanding the hidden architecture of reality itself. There's something out there, an invisible force so immense it's pulling entire galaxies, including our own, toward an uncharted point in space. Meet the Great Attractor, one of the universe's most baffling mysteries. Hidden behind the thick dust and stars of the Milky Way's galactic plane, this colossal gravitational anomaly exerts a pull so strong, it's redirecting the motion of thousands of galaxies, including the local group we call home. Picture a cosmic whirlpool, its current dragging everything in its reach toward an unseen center. But what exactly lies at its heart? For decades, astronomers struggled to study it directly because our own galaxy's dense core blocks the view. Yet through indirect observations tracking the peculiar motion of galaxies streaming toward it, they pieced together a startling truth. The Great Attractor isn't just a single massive object. It's part of something far grander. Enter the Laniakea supercluster, a sprawling network of galaxies spanning over 500 million light-years. Within this vast cosmic metropolis, the Great Attractor acts like a gravitational anchor, a focal point where entire galaxy clusters converge. But here's where it gets even stranger. The mass we can see the galaxies and gas clustered in this region doesn't fully explain its immense pull. There's something else at play, something invisible amplifying its gravity. Could it be an unprecedented concentration of dark matter, or is there an even larger structure lurking beyond, tugging on the Great Attractor itself? Some theories suggest the Shapley supercluster, a gargantuan assembly of galaxies even farther away, might be influencing this cosmic dance. The more we learn, the more questions arise. Why is the Milky Way, along with countless other galaxies, hurtling toward this spot at over 2 million kilometers per hour? What does this mean for the future of our cosmic neighborhood? And if dark matter is the hidden architect here, how does it shape such colossal structures without leaving a visible trace? Every clue we uncover peels back another layer of the mystery. Recent advances in infrared and radio astronomy are finally piercing the veil of dust that long obscured our view. New maps reveal intricate flows of galaxies, all converging like rivers into an unseen ocean. Yet the Great Attractor's core remains elusive, a shadowy enigma that challenges our understanding of gravity, motion, and the large-scale structure of the universe. One thing's certain, this isn't just a distant curiosity. It's a reminder that even as we map the cosmos, vast unknowns still pull at the edges of our knowledge. The Great Attractor forces us to confront a humbling truth. We're not just observers of the universe's grand design. We're participants in its motion, caught in a gravitational current we're only beginning to chart. And somewhere beyond the Milky Way's glow, the answer waits, pulling us closer with every passing moment. Stretching across the vast emptiness of space like an intricate network of rivers, cosmic filaments weave the universe together on a scale so enormous, it challenges comprehension. These are not just delicate threads of gas and dust, they're colossal highways, some spanning hundreds of millions of light years, funneling the raw materials of creation into the densest regions of the cosmos. Imagine standing at the edge of one of these filaments, watching as galaxies glide along its length, pulled by gravity's invisible hand toward bustling intersections where galaxy clusters collide and merge. This is how the universe builds its grandest structures, not randomly, but along these precise, luminous roads. What's truly astonishing is how active these filaments are. They're not passive scaffolding, they're dynamic, pulsing with energy. Gas streaming along these channels heats up to millions of degrees, glowing faintly in X-rays as it rushes toward galactic hubs. And here's the twist, this superheated gas doesn't just feed galaxies, it controls their fate. When a galaxy sits along a filament, it's like a city at the crossroads of a major trade route, constantly replenished with fresh fuel for star formation. But galaxies stranded in the voids between filaments, they're like isolated towns cut off from supplies, their star-forming gas slowly draining away. Telescopes like Hubble have given us breathtaking glimpses of this cosmic web, showing galaxies perfectly aligned along these filaments as if strung on a celestial necklace. But the upcoming James Webb Space Telescope promises to reveal even more, peering deeper into these structures to uncover how the first galaxies were born within them. Already, simulations suggest that filaments acted as cosmic wombs in the early universe, funneling gas into dense pockets where gravity could ignite the first stars. Without these channels, the universe might have remained a dark, empty sea. Yet filaments also have a destructive side. When galaxies are dragged into crowded clusters along these highways, they often face violent ends, stripped of their gas, their star formation snuffed out by the brutal tides of larger neighbors. It's a dramatic paradox. The same forces that give life to galaxies can also starve them. And lurking within it all is dark matter, the unseen skeleton that gives these filaments their shape, guiding the flow of ordinary matter like an invisible conductor. The more we learn, the clearer it becomes. If we want to understand why some galaxies blaze with young stars while others fade into quiet obscurity, we must follow these filaments. They're not just backdrops to cosmic history, they're the architects of it, sculpting the destiny of everything from the smallest dwarf galaxy to the largest supercluster. And as we map their intricate paths, we're tracing the very blueprint of the universe itself. While cosmic filaments and galaxy clusters dominate our maps of the universe, the true giants of space aren't the structures we see, they're the staggering voids between them. Imagine standing in the middle of one of these cosmic deserts, where the nearest galaxy is so distant, its light would take hundreds of millions of years to reach you. These voids aren't just empty pockets, they're active players in shaping the universe, stretching across unfathomable distances like bubble walls in a froth of galaxies. And here's what's wild: without these voids, the universe as we know it wouldn't exist. The math is startling. While filaments and superclusters make up just 10% of the cosmos's volume, voids occupy nearly 80%. That means most of the universe isn't filled with glittering stars or swirling nebulae. It's an unimaginably vast nothingness. But nothing might be the wrong word. Even these voids aren't completely empty. Floating within them are a few lonely galaxies, rogue planets, and wisps of gas so thin they'd make Earth's atmosphere seem dense by comparison. And yet, these near-vacuum regions hold immense power. Here's how it works: as the universe expands, voids grow faster than denser regions, acting like cosmic pressure chambers. Their gravitational push isn't strong enough to hold matter, so they effectively repel it, herding galaxies toward the filaments and clusters at their edges. It's like a cosmic game of pinball, where voids serve as the bumpers, redirecting galaxies into the busy highways of the cosmic web. Some astronomers call this phenomenon void pushing, and it may explain why our local group of galaxies is moving so quickly toward the Great Attractor. But the mysteries don't end there. Voids might be hiding clues to some of physics' biggest puzzles. Their extreme emptiness makes them perfect laboratories for testing theories about dark energy, the mysterious force accelerating the universe's expansion. One provocative idea suggests that voids could contain traces of exotic particles or even wrinkles in space-time linking to other dimensions. While that sounds like science fiction, it's grounded in real math. Some models of string theory predict that voids' low-density environments might allow hidden dimensions to briefly unfurl. The eeriest part: voids are growing. As dark energy drives the universe apart, these empty regions stretch faster than anywhere else, becoming even more barren over time. Billions of years from now, the voids between superclusters may expand so much that future civilizations, if they exist, would see only an inky black sky. Their neighboring galaxies vanished over the horizon of spacetime. It's a humbling reminder that the universe isn't just defined by what's there, but by what isn't. And as we peer deeper into these cosmic absences, we're not just mapping emptiness, we're uncovering the hidden rules that govern everything. Zoom in far enough, past galaxies, past stars, past even atoms, and reality itself starts to unravel. What looks smooth and predictable to our eyes becomes a turbulent, seething chaos at the smallest scales imaginable. This is quantum foam, the hypothetical froth at the very foundation of spacetime, where the rules of gravity and quantum mechanics collide in a frenzy of creation and destruction. Picture an ocean during a storm, but instead of waves, you have spacetime itself bubbling with tiny, ephemeral black holes and wormholes, popping in and out of existence so fast they leave no trace. It's as if the universe is constantly remaking itself beneath our feet, one infinitesimal piece at a time. The idea of quantum foam isn't just wild speculation. It's a direct consequence of quantum mechanics and Einstein's theory of relativity. At these unimaginably small scales, the energy of empty space isn't calm. It's a maelstrom of virtual particles appearing and vanishing in fractions of a second, warping spacetime into a foam-like structure. Think of it like static on an old television screen. From a distance, the image looks smooth, but up close, it's a storm of flickering pixels. Only here, the pixels are fluctuations in the fabric of reality itself. But here's where it gets even stranger. Quantum foam might hold the key to some of the universe's biggest mysteries. Take dark energy, for example, the force accelerating the expansion of the cosmos. Some theories suggest that the frothy energy of quantum foam could be fueling this expansion, like a hidden engine pushing the universe apart from the inside. Then there's black holes, the singularity at their core where gravity becomes infinite and spacetime breaks down. Might not be a point at all, but a knot of quantum foam churning endlessly. The catch: we can't observe quantum foam directly. Its bubbles are thought to be trillions of times smaller than an atom, far beyond the reach of even our most powerful microscopes. But scientists aren't giving up. They're looking for its fingerprints in the ripples of gravitational waves, hunting for tiny hiccups in spacetime that could betray its foamy nature. Others are smashing particles together at near light speeds, hoping to glimpse distortions that hint at this underlying turbulence. If quantum foam is real, it would rewrite our understanding of reality's building blocks. No longer would spacetime be a passive stage for the universe's drama. It would be an active participant, bubbling with energy and possibility, and that raises profound questions. Could these fleeting wormholes connect distant parts of the universe, even for an instant? Could the foam's chaos hold clues to a deeper theory that unites gravity and quantum mechanics? For now, quantum foam remains just beyond our grasp, a tantalizing whisper at the edge of physics. But every experiment, every observation, brings us closer to uncovering the truth that the universe, even in its quietest moments, might be anything but still. Black holes aren't just the universe's most destructive forces, they're also its most surprising architects. Picture a supermassive black hole at the heart of a galaxy. Its gravity so intense, not even light can escape. Yet this same destructive power sculpts the cosmos in ways we're only beginning to understand. Take star formation, for example. When a black hole's gravitational tides pull gas clouds into orbit, they don't always vanish forever. Instead, those swirling clouds can collide, compress, and ignite, sparking the birth of new stars. It's like throwing a stone into a pond and watching the ripples create patterns you never expected. But black holes don't just build, they also regulate. Supermassive black holes lurking in galactic centers act like cosmic thermostats. When they feed on surrounding gas, they don't just swallow it quietly. They unleash torrents of energy, jets of plasma and radiation so powerful they can heat up interstellar gas across thousands of light years. This cosmic feedback prevents galaxies from growing too fast, like a safety valve keeping the universe in balance. Without it, galaxies would bloat uncontrollably, their stars burning out in a frenzied rush. Then there's spacetime itself. Black holes don't just bend it, they twist it into knots. Near the event horizon, time slows to a crawl and space stretches like taffy. This warping doesn't stay confined. It ripples outward, influencing the motion of stars and even the trajectory of entire galaxies. When two black holes collide, they send gravitational waves racing through the cosmos, distortions in space-time so subtle, we only detected them for the first time in 2015. These waves are like cosmic fingerprints, revealing how black holes shape the universe in their violent mergers. And let's talk about scale. The first image of a black hole's shadow, captured by the Event Horizon Telescope in 2019, wasn't just a triumph of technology, it was a glimpse into the engine room of the cosmos. That glowing ring of light, its photons trapped in orbit, a visual echo of the black hole's immense gravity. But what's truly staggering is how small that shadow appears compared to its influence. The black hole at the center of the Milky Way, Sagittarius a star, weighs 4 million times more than our Sun, yet it governs the orbits of hundreds of billions of stars around it. Here's the kicker: black holes might even be the glue holding the cosmic web together. Simulations suggest that the earliest supermassive black holes, born in the chaotic infancy of the universe, could have seeded the growth of galaxies by attracting vast reservoirs of gas. Their gravitational pull acted like cosmic anchors, drawing matter into the filaments and nodes we see today. Without them, the universe might be a scattered, formless sea of dim stars. So the next time you think of a black hole as just a cosmic vacuum, remember, it's more like a sculptor, a regulator, and a puppeteer all at once. From igniting stars to guiding galaxies, these invisible giants are the unseen hands shaping the universe's grand design. And with every new discovery, we're peeling back another layer of their mystery, revealing just how deeply they're woven into the fabric of reality. If dark matter is the universe's hidden scaffolding, then dark energy is its silent engine, an enigmatic force not just expanding the cosmos, but doing so at an ever-increasing pace. Picture a balloon inflating faster and faster, not because you're blowing harder, but because the rubber itself is changing, stretching space from within. That's the puzzle astronomers faced in the late 1990s when distant supernova revealed something shocking. The universe wasn't just growing, its expansion was accelerating. The discovery flipped cosmology on its head, earning researchers the Nobel Prize and leaving us with a haunting question: what unseen force is stronger than gravity itself? The numbers are staggering. Dark energy makes up roughly 68% of the universe's total content, dwarfing both dark matter and ordinary matter combined. Yet unlike dark matter, which clumps around galaxies, dark energy appears to be woven into the fabric of space itself, a property of the vacuum that grows stronger as the universe expands. Imagine pouring water into a cup, only to watch the cup grow larger with each drop. Dark energy behaves like that, its influence increasing as space stretches. But what is it? The leading theory points to Einstein's cosmological constant, an idea he once called his greatest blunder, suggesting empty space has an intrinsic energy pushing outward. Others propose a dynamic field, nicknamed quintessence, that could change over time. Then there are the wilder possibilities. Could dark energy be evidence of extra dimensions leaking gravity into our universe? Or a sign that Einstein's theory of gravity needs rewriting on cosmic scales? The stakes couldn't be higher. Dark energy doesn't just shape the universe, it will decide its fate. If it continues unchecked, galaxies beyond our local group will eventually vanish over the cosmic horizon, their light stretched beyond detection. In tens of billions of years, astronomers in our galaxy might peer into an empty sky with no evidence other universes ever existed. Some models suggest a more violent end, the Big Rip, where dark energy grows so dominant it tears apart galaxies, stars, even atoms in a final, catastrophic instant. Yet for all its power, dark energy leaves almost no trace to study. Unlike dark matter, which bends light and tugs on galaxies, dark energy's effects only emerge across vast distances. To catch its fingerprints, scientists map millions of galaxies, measure ancient supernovae, and even listen for echoes of the Big Bang in the cosmic microwave background. Upcoming telescopes like the Vera Rubin Observatory and the Euclid Space Mission aim to chart its influence with unprecedented precision, hunting for tiny deviations that might reveal its true nature. Here's the twist: dark energy might not be constant. Recent observations hint it could vary over time or space, a clue that would upend our understanding of physics. If confirmed, it would mean the universe's expansion isn't just accelerating, it's evolving, following rules we haven't yet deciphered. That's the beauty and frustration of dark energy. It's the ultimate cosmic wildcard, a reminder that even as we unravel the universe's mysteries, the biggest questions still loom in the dark. What if our universe isn't the only one? Imagine a cosmic froth bubbling with countless other universes, each with its own unique laws of physics, some barren, some bursting with strange forms of life, others collapsing instantly under their own impossible rules. This isn't science fiction. It's the multiverse hypothesis, one of the most daring ideas in modern cosmology. And while it might sound like fantasy, it's grounded in real science, from the explosive aftermath of the Big Bang to the mind-bending math of string theory. Take cosmic inflation, for example. This theory suggests that in the first fractions of a second after the Big Bang, space expanded faster than light, stretching quantum fluctuations into vast cosmic landscapes. But here's the twist: inflation might not have stopped everywhere. Some regions of space could still be inflating eternally, spawning new universes like bubbles in an endless cosmic foam. Each of these bubble universes might cool differently, settling into unique physical laws. In some, gravity could be 10 times stronger. In others, atoms might never form. Ours just the lucky lottery ticket where everything lined up perfectly for stars, planets, and life. String theory takes this even further. It proposes that the fundamental building blocks of reality aren't particles but tiny, vibrating strings. And the way these strings vibrate could determine everything from the strength of gravity to the existence of time itself. But here's the catch. The math suggests there aren't just a handful of possible vibrations. There could be 10 to the power of 500 possible configurations. That's a 1 followed by 500 zeros. If each configuration represents a different universe, then the multiverse isn't just likely, it's inevitable. Then there's quantum mechanics, where every possible outcome of an event might play out in a branching web of realities. Did you turn left at the intersection this morning? In another universe, you turned right. While this many worlds interpretation is controversial, it hints at a cosmos far weirder than we ever imagined. But why does any of this matter? Because the multiverse could solve one of science's biggest puzzles, the fine-tuning problem. Our universe's constants, the strength of gravity, the mass of an electron, are exquisitely balanced for life. Tweak them even slightly and stars wouldn't shine, chemistry wouldn't work, and life as we know it would be impossible. If there are infinite universes with infinite variations, ours isn't a miracle. It's just the one where the dice rolled in our favor. Of course, the multiverse remains speculative. We can't observe these other universes directly, and some critics argue it's more philosophy than science. Yet the idea pushes the boundaries of imagination, forcing us to confront profound questions. Are we the only version of reality, or just a single thread in an infinite tapestry? If other universes exist, do they have their own astronomers staring into the void, wondering the same thing? For now, the multiverse remains a tantalizing possibility, a cosmic, What if that challenges everything we think we know? But whether it's proven or not, one thing's certain: the universe or universes hold mysteries we've only begun to explore. And every theory, no matter how wild, brings us closer to understanding our place in the grand scheme of things. Einstein's theory of relativity gave us a radical idea that space isn't just an empty stage, but a flexible fabric that bends under the weight of matter. And when light travels through this warped landscape, it doesn't move in straight lines. It follows the curves like a car winding down a mountain road. That's gravitational lensing in action, a cosmic illusion where massive objects, like galaxies or black holes, act as natural magnifying glasses, distorting and amplifying the light from objects behind them. It's as if the universe handed astronomers a free telescope, one far more powerful than anything we could build. The most stunning part: lensing doesn't just reveal distant galaxies, it unveils the invisible. When light bends around a galaxy cluster, the amount of distortion tells scientists how much mass is there, including the dark matter we can't see. It's like watching a shadow puppet show. You might not see the hands casting the shapes, but their influence is unmistakable. Some of the most precise dark matter maps ever made come from studying these twisted arcs of light, tracing the hidden scaffolding that holds the cosmos together. But lensing isn't just a tool for mapping the unseen, it's a time machine. Take the Hubble Space Telescope's Frontier Fields project, which used galaxy clusters as natural lenses to peer deeper into space than ever before. One cluster, Able 1689, magnified a galaxy so faint its light had been traveling for over 13 billion years, a snapshot of the universe in its infancy. Without lensing, that galaxy would have remained a whisper in the dark. Then there's the eerie beauty of Einstein rings, perfect circles of light formed when a distant galaxy aligns precisely behind a massive foreground object. These rare cosmic bullseyes aren't just breathtaking, they're precision instruments. By measuring the ring's size, astronomers can calculate the mass of the lensing object down to the last star. And sometimes lensing plays tricks on us, creating multiple images of the same object scattered across the sky like a cosmic hall of mirrors. The future of lensing is even more exciting. Upcoming telescopes like the Nancy Grace Roman Space Telescope will hunt for thousands of new lensed galaxies, while AI sifts through data to spot distortions human eyes might miss. With each discovery, we're not just seeing farther, we're decoding the universe's hidden blueprint, one bent beam of light at a time. The cosmic microwave background isn't just ancient light, it's a time capsule, a whisper from the universe's very first moments. Picture this: everywhere you look, in every direction, space is filled with a faint glow, a relic of a time when the cosmos was a seething plasma, hot and dense as the heart of a star. That glow cooled over billions of years to just a few degrees above absolute zero, is the afterimage of the Big Bang itself. But it's not just a uniform haze. Embedded within it are tiny ripples, temperature variations no larger than 1 part in 100,000. And those minuscule fluctuations, they're the blueprints for everything we see today. What's astonishing is how much these subtle wrinkles tell us. When the Planck and WMAP satellites mapped the CMB in unprecedented detail, they weren't just taking a picture, they were decoding the universe's birth certificate. Those slightly warmer and cooler patches correspond to regions where matter was ever so slightly denser or sparser. Over cosmic time, gravity amplified those differences, pulling dark matter into clumps that would eventually anchor galaxies. In other words, the grand tapestry of the cosmic web, the galaxies, clusters, and voids we marvel at today, was woven from these primordial seeds. But the CMB holds even deeper secrets. Its patterns reveal the universe's age with pinpoint accuracy, 13.8 billion years old. They tell us how fast space is expanding, how much dark matter and dark energy fill the cosmos, even how matter itself is distributed on the largest scales. It's like finding a single fossil and reconstructing an entire evolutionary tree. And perhaps most mind-bending of all, the CMB gives us a glimpse of inflation, the explosive expansion thought to have occurred in the first fraction of a second after the Big Bang. The way those temperature fluctuations are distributed across the sky matches predictions of inflation theory almost perfectly, as if the universe left us a deliberate clue. Yet for all we've learned, the CMB still guards mysteries. Why is one half of the sky slightly cooler than the other? Could that hint at a pre-Big Bang era, or is it just a statistical fluke? And what about the so-called cold spot, a puzzling region far larger and chillier than expected? Some speculate it might be evidence of a collision with another universe in the multiverse, though others argue it's just a trick of the data. Here's what's truly humbling. When you look at the CMB, you're seeing the oldest thing humanity will ever observe. Older than the first stars, older than the first atoms. It's light that began its journey before Earth, before the Milky Way, before even the simplest molecules existed. And it's still arriving, carrying messages from a time when the universe was a newborn, its destiny unwritten. Every new observation, every refined measurement peels back another layer, bringing us closer to answering the ultimate question: where did all this come from? The cosmic microwave background isn't just a relic of the past, it's a roadmap to the future. Long before galaxies or stars existed, the universe was a roiling ocean of sound. Imagine the cosmos not as the silent void we know today, but as a vibrating sea of plasma where pressure waves raced outward at half the speed of light. These were no ordinary sound waves, they were the baryon acoustic oscillations, primordial ripples frozen in time, now serving as one of nature's most precise measuring tapes. Here's how it happened. In the first few 100,000 years after the Big Bang, the universe was so hot and dense that matter and light were locked in a constant tug of war. Photons pushed against protons and electrons, creating regions of slightly higher and lower density, like the crests and troughs of a sound wave moving through air. But when the universe cooled enough for atoms to form, light broke free in what we call the cosmic microwave background, and those pressure waves became suddenly, permanently imprinted on the distribution of matter. The result, a vast cosmic fingerprint, with galaxies today tending to cluster at specific distances from one another roughly 500 million light-years apart, like beads strung along the echoes of those ancient vibrations. What makes BAOs so valuable to astronomers is their predictability. Unlike other cosmic yardsticks that can warp or fade over time, these oscillations remain pristine, acting as a standard ruler etched into the fabric of space. By measuring how much this ruler appears stretched or compressed at different eras of the universe, scientists can track how expansion has accelerated or slowed. And here's where dark energy enters the picture. When researchers compared BAOs from the early universe to those in more recent epochs, they found the expected distance between galaxies had grown larger than predicted, direct evidence that something was pushing space apart faster and faster. But BAOs aren't just about dark energy. They're also a stress test for our entire understanding of cosmic evolution. Some theories suggest that if gravity behaves differently on vast scales, or if dark energy isn't constant but evolves over time, BAOs should reveal subtle deviations in the clustering of galaxies. Projects like the Dark Energy Spectroscopic Instrument, DAISY, are mapping millions of galaxies to hunt for these clues, creating 3D atlases of the universe where every measured BAO is another data point in the grandest experiment of all. Perhaps most astonishing is how these frozen sound waves connect us to the universe's infancy. When you look at a BAO map, you're seeing the aftermath of vibrations that last resonated when the cosmos was a swirling plasma, before the first atoms, before the first light. It's as if the universe left us a message in Morse code, written not in dots and dashes, but in the precise arrangement of galaxies across billions of years. And with every new survey, every sharper measurement, we're tuning in clearer to that primordial broadcast decoding the secrets of expansion, dark energy, and the fate of everything. Neutrinos are the universe's most elusive architects, particles so ghostly, they pass through entire planets like they aren't even there. Every second, trillions of them stream through your body, leaving no trace, as if you're nothing more than a wisp of smoke to them. Born in the hearts of stars, the fury of supernova, and even the Big Bang itself, these nearly massless particles carry secrets about the cosmos that light alone could never reveal. And while they barely interact with matter, their collective gravity might be quietly sculpting the universe on scales we're only beginning to grasp. Think of neutrinos as cosmic ghosts slipping through walls, stars, even entire galaxies without a whisper. Unlike dark matter, which clumps around galaxies like invisible scaffolding, neutrinos zip through space at nearly the speed of light, their paths barely bending under gravity's pull. Yet over billions of years, even their minuscule mass adds up. Simulations show that streaming neutrinos could subtly suppress the growth of small galaxies, acting like a cosmic sieve that lets only the densest structures form. It's as if the universe has an invisible hand, gently smoothing out the distribution of matter on the largest scales. But catching these phantoms is no easy task. Detectors like IceCube buried deep in Antarctic ice and Super Kamiok and a colossal tank of ultra-pure water beneath Japan lie in wait for the rare moment a neutrino collides with an atom. When it happens, the result is a fleeting burst of light, a cosmic fingerprint. Some of these neutrinos have traveled for billions of years, carrying messages from the most violent events in the universe. In 2017, IceCube spotted a neutrino from a blazar, a supermassive black hole spewing jets of particles across the cosmos. That single detection opened a new window into the high-energy universe, proving these particles could trace cosmic cataclysms light alone couldn't penetrate. Here's the twist: neutrinos might be the missing link between the visible and invisible universe. Some theories suggest they could be connected to dark matter. Perhaps a fraction of dark matter is made of sterile neutrinos, an even more elusive variant that interacts only through gravity. Others propose that neutrinos could explain why the universe has more matter than antimatter, a mystery known as leptogenesis. If neutrinos behaved slightly differently in the early cosmos, they might have tipped the scales, ensuring stars, planets, and eventually life could exist. The deeper we look, the more these ghostly particles defy expectations. They oscillate, changing flavors between electron, muon, and tau types mid-flight, a quantum quirk that hints at physics beyond the standard model. And their tiny masses, once thought to be zero, could hold clues about the universe's first seconds. If neutrinos gained mass through interactions with the Higgs field, they might carry echoes of that primordial moment when symmetry broke and the laws of physics as we know them snapped into place. So the next time you gaze at the night sky, remember, you're not just seeing stars and galaxies, you're witnessing the aftermath of an unseen dance, where trillions of invisible particles have been shaping the cosmos since the very beginning. And with every neutrino detected, we're pulling back another layer of the universe's most enduring mysteries. Einstein's theory of general relativity has been the bedrock of modern physics for over a century, but what if it's incomplete? A small but passionate group of scientists are asking that very question, suggesting that the mysteries of dark matter and dark energy might not be evidence of invisible substances, but rather clues that gravity itself works differently on cosmic scales than we've assumed. Entanglement modified Newtonian dynamics, a radical rethink of how gravity behaves when distances stretch to the vastness between galaxies. At the heart of this idea is a simple observation: galaxies rotate faster than they should. According to Newton and Einstein, stars on the outer edges of galaxies ought to move slower, like planets farther from the Sun. Yet when astronomers measured their speeds, they found stars whipping around at nearly the same velocity regardless of distance, as if some unseen mass were holding them in place. Mainstream physics chalks this up to dark matter's gravitational pull, but Mund proposes something far bolder. Maybe gravity doesn't weaken as sharply over large distances as our equations predict. Instead, it plateaus, providing just enough extra tug to explain galactic rotation without invoking invisible particles. The implications are staggering. If Mund is correct, entire chapters of cosmology, dark matter halos, WIMP searches, even the cosmic web's dark scaffolding could be redrawn. Proponents point to intriguing successes, like Mund's uncanny ability to predict the rotation curves of certain galaxies without any free parameters. There's even evidence that some dwarf galaxies, where dark matter models struggle, align better with Mund predictions. It's as if the universe left us a trail of breadcrumbs, hinting that gravity's rules might change when accelerations dip below a critical threshold, about 100 billionth of the force you feel when your phone drops to the floor. Yet Mund faces formidable challenges. While it elegantly explains galaxy rotations, it stumbles when confronted with the bullet cluster, a cosmic collision where most visible matter clumped in one region, while gravitational lensing revealed mass displaced elsewhere, exactly as dark matter would predict. Then there's cosmic acceleration. Mund wasn't designed to explain dark energy's role in universal expansion, forcing theorists to graft on additional hypotheses. Critics argue this makes Mund less elegant than the dark matter paradigm, which tackles both galaxy dynamics and cosmic structure with a single unseen ingredient. The debate isn't just academic, it cuts to the core of how science progresses. Every time an anomaly arises, like galaxies mysteriously devoid of dark matter or odd gravitational lensing patterns, both camps scramble to adjust their models. Dark matter theorists invoke complex distributions of invisible particles, while Mund supporters tweak their equations. What's fascinating is how each side's fixes inadvertently borrow from the other, blurring the lines between rival paradigms. Some researchers now explore hybrid theories where modified gravity and dark matter coexist, or where gravity's behavior emerges from deeper quantum principles we haven't yet uncovered. Perhaps the most thrilling aspect of this controversy is what it reveals about the scientific process. Mund forces us to confront uncomfortable questions. Have we been too quick to accept dark matter as dogma? Or is modifying gravity a bridge too far, risking the foundations of physics to avoid unseen substances? Either way, the tension between these ideas is fertile ground for discovery. Upcoming experiments like the Vera Rubin Observatory's ultra-precise galaxy surveys or space-based tests of gravity's strength at different scales could tip the scales decisively. Until then, the universe keeps its secrets close, reminding us that even our most cherished theories are provisional, waiting for the next breakthrough to rewrite the rules. There's a theory so strange it makes the multiverse sound tame. What if everything you see, touch, and experience is nothing more than an elaborate illusion? Not a computer simulation, not a dream, but a cosmic hologram, where the three-dimensional universe we perceive is actually encoded on a distant two-dimensional surface. This is the holographic principle, an idea born from the fiery edges of black hole physics, now challenging our deepest assumptions about reality itself. It all started with a paradox. When Stephen Hawking discovered black holes emit radiation, he realized they must slowly evaporate, raising a terrifying question. What happens to all the information swallowed by the black hole? Quantum mechanics insists information can't be destroyed, yet general relativity says it vanishes forever behind the event horizon. The solution may be the information isn't lost. Maybe it's smeared across the black hole's surface, like a cosmic DVD encoding everything that fell inside. Take this idea further, and you arrive at an astonishing possibility. If a black hole's interior can be described entirely by data on its boundary, could the same be true for the entire universe? Think of it like a movie screen. The images appear three-dimensional, full of depth and movement, but they're really just flat projections. Similarly, the holographic principle suggests that particles, forces, even space and time might emerge from a hidden, lower-dimensional reality. Every event in our world, a supernova exploding, a leaf falling, could be the shadow of information processing happening on some unimaginable distant surface. The math behind this is both elegant and bewildering. In the 1990s, physicist Juan Maldacena discovered a concrete example. A theoretical universe with 5 dimensions of space-time could be perfectly mirrored by a 4-dimensional theory without gravity. The two descriptions were mathematically equivalent, like translating a novel into another language without losing a single nuance. If our universe follows similar rules, it would mean gravity, quantum fields, even the fabric of space itself aren't fundamental. They're secondary effects emerging from deeper, simpler laws. But how could this possibly be tested? Surprisingly, scientists are looking for clues in the cosmic microwave background, the afterglow of the Big Bang. If the universe is holographic, its fluctuations might carry subtle imprint statistical anomalies that betray its true, lower-dimensional nature. Other experiments probe the limits of quantum entanglement, searching for hints that space-time itself is stitched together by information. The implications are staggering. If the holographic principle is true, then the universe isn't just stranger than we imagine, it's stranger than we can imagine. Reality as we know it would be a kind of collective hallucination, a shared projection from a boundary we can't see or touch. It would mean the cosmos operates like a quantum computer, with every event, every particle, just a calculation unfolding on a vast cosmic hard drive. Yet for all its brilliance, the holographic principle leaves us with more questions than answers. What exactly is this mysterious two-dimensional surface? How does it encode the richness of our three-dimensional experience? And if we're living in a hologram, who or what is holding the projector? For now, these mysteries linger at the edge of science, daring us to rethink not just the universe, but the very nature of existence itself. Deep beneath the streets of Geneva, inside a circular tunnel large enough to fit a subway system, protons smash together at nearly the speed of light. These collisions at CERN Large Hadron Collider don't just recreate conditions from the early universe, they momentarily birth substances so bizarre, they defy everything we know about matter. Take quark-gluon plasma, for instance. This primordial soup, which last existed microseconds after the Big Bang, isn't a solid, liquid, or gas. It's a state where protons and neutrons melt into their fundamental ingredients, quarks and gluons, flowing freely like a cosmic liquid with zero viscosity. When heavy ions collide in the LHC, temperatures soar to over 5 trillion degrees Celsius, 100,000 times hotter than the sun's core, and for the briefest instant, this exotic matter flickers back into existence. But quark-gluon plasma is just the beginning. Theoretical physicists speculate about even stranger forms of matter, particles that could unlock the universe's greatest puzzles. Actions, for example, are hypothetical particles so lightweight they barely interact with ordinary matter. Yet if they exist, they might solve two mysteries at once: the nature of dark matter and why the universe has so little antimatter. Unlike traditional dark matter candidates, actions wouldn't clump in halos around galaxies. They'd behave more like an invisible quantum mist, permeating space with waves so subtle only ultra-sensitive detectors like the Action Dark Matter experiment might catch their whisper. Then there's negative matter, a substance with negative mass that repels rather than attracts gravity. While it sounds like science fiction, Einstein's equations allow for its existence. If harnessed, negative matter could theoretically stabilize wormholes, making interstellar shortcuts possible, or even enable warp drives by bending spacetime into bubbles that move faster than light. NASA Eagleworks Lab has explored these ideas through preliminary experiments, testing whether we might one day engineer the fabric of reality itself. The hunt for exotic matter isn't confined to Earth. Telescopes scan the cosmos for clues in the most violent events imaginable. Neutron stars, those ultra-dense corpses of dead suns, squeeze matter so tightly that atoms collapse into a sea of neutrons with possible pockets of strange quark matter, a phase where quarks themselves rearrange into configurations never seen on Earth. Meanwhile, magnetars, neutron stars with magnetic fields a quadrillion times stronger than Earth's, might host yet unknown states of matter where physics operates under extreme rules. What makes this search so urgent is how these substances could redefine reality. Dark matter might not be a single particle but an entire shadow sector of exotic matter, invisible yet shaping the cosmos. Quantum anomalies in lab experiments hint at particles beyond the standard model, suggesting we've only scratched the surface of matter's possibilities. And if even one of these theoretical forms is confirmed, it wouldn't just fill a gap in our equations, it would open doors to technologies and understandings we can barely envision. The universe, it seems, still holds its most astonishing secrets just out of sight, waiting for the right experiment, the right observation to pull them into the light. The universe is unimaginably vast with hundreds of billions of galaxies, each containing billions of stars, most likely orbited by even more planets. Given those staggering numbers, the math suggests intelligent life should be common. So where is everyone? This is the heart of the Fermi Paradox, a question that's haunted scientists for decades. If the cosmos is so full of potential, why does it feel so empty? The silence isn't just puzzling, it's unsettling, because every possible answer forces us to confront uncomfortable truths about our place in the universe, and perhaps even our future. One explanation is chillingly simple. Advanced civilizations might not survive long enough to make contact. This idea, known as the Great Filter, suggests there's some catastrophic hurdle: nuclear war, runaway AI, ecological collapse, that wipes out societies before they can spread beyond their home worlds. If true, the filter could still lie ahead of us, a looming bottleneck waiting to snuff out humanity's reach for the stars. Alternatively, we might have already passed it, making us the rare exception in a cosmic graveyard. Either possibility is humbling. Then there's the dark forest theory, a concept borrowed from sci-fi but grounded in grim logic. Imagine the universe as a vast, shadowy woodland where every civilization hides, terrified of revealing its location. In this scenario, broadcasting signals or expanding outward could invite destruction from older, more advanced species lurking in the cosmic underbrush. It's a paranoid but plausible explanation for the silence, one where survival means staying quiet forever. But what if aliens aren't hiding or extinct? What if they've simply evolved beyond our recognition? Some theorists propose that advanced life might ditch biology altogether, transitioning into superintelligent AI or even pure energy. These post-biological beings could exist all around us, operating on scales or dimensions we can't perceive, like ants unaware of the internet humming beneath their feet. The paradox might also hinge on the universe's invisible architecture. Cosmic filaments could funnel life into isolated pockets, while dark energy pushes galaxies apart faster than civilizations can bridge the gaps. Or perhaps the answer is even stranger. We're living in a simulation, and the programmers never bothered to fill the universe with other players. Yet amidst these bleak possibilities, there's hope. New telescopes are scanning exoplanet atmospheres for biosignatures, while projects like SETI deploy increasingly sophisticated tools to eavesdrop on cosmic chatter. Maybe we're simply early to the party, with the galaxy's great civilizations yet to emerge. Or perhaps one day we'll crack the paradox and realize we were never alone, just listening for the wrong signals all along. Until then, the silence remains a riddle echoing across the stars. Time crystals sound like something ripped straight from science fiction, but they're very real, and they're rewriting the rules of physics as we know them. Unlike ordinary crystals where atoms arrange themselves in repeating patterns in space, time crystals flip the script. Their structure repeats in time, cycling through states indefinitely without losing energy. Imagine a snowflake that doesn't just sit there but pulses, oscillating between shapes forever, never winding down. That's the surreal beauty of these structures. They exist in a perpetual dance, defying one of the universe's most fundamental laws, the inevitable march toward equilibrium. The idea was first proposed in 2012 by Nobel laureate Frank Wilczek, who dared to ask, could matter exhibit periodic motion not just in space but in time itself? Skeptics dismissed it as impossible. After all, perpetual motion machines are forbidden by thermodynamics. Yet by 2017, labs at Harvard and the University of Maryland had done the unthinkable, creating time crystals using chains of ions and diamond impurities chilled to near absolute zero. These weren't theories anymore. They were tangible, measurable realities, ticking like quantum metronomes in defiance of entropy. Here's where it gets even weirder. Time crystals don't just ignore equilibrium, they exist because of it. Normally, if you nudge a system, it settles back down. But time crystals, when gently pulsed, respond by oscillating at a different frequency than the force applied. It's like pushing a swing and watching it move sideways instead. This bizarre behavior emerges from quantum entanglement, where particles become so deeply linked that their collective state locks into a rhythm no single particle could sustain alone. Could these strange structures exist beyond the lab? Some physicists speculate that time crystals might form naturally in extreme cosmic environments, perhaps in the crushing gravity of neutron stars or the turbulent aftermath of the Big Bang. If so, they could be silently influencing quantum processes, even altering how space-time behaves on microscopic scales. One wild theory suggests that vacuum fluctuations, the quantum froth of empty space, might contain fleeting time crystal-like order, a hidden cadence beneath reality's surface. The implications are staggering. Time crystals could revolutionize quantum computing, acting as flawless memory banks immune to decoherence. They might even help us probe the boundaries of physics, offering clues about how time itself emerges from the quantum realm. But the most thrilling possibility that we've only scratched the surface. If matter can crystallize in time, what other impossible phases are waiting to be discovered? The universe, it seems, still holds wonders that defy not just our expectations, but our very definitions of what's possible. What if everything around you, the stars, the trees, even the hands you're using to watch this video, aren't real? Not in the philosophical sense, but in the most literal way possible. The simulation hypothesis suggests our universe might not be the base layer of reality, but an incredibly advanced digital construct, like a hyper-realistic video game built by some unfathomable intelligence. This isn't just sci-fi. Musing respected thinkers like Nick Bostrom and Elon Musk have seriously entertained the idea, and the math behind it is eerily compelling. Bostrom's famous trilemma lays out the unsettling possibilities. First, almost all civilizations go extinct before developing simulation technology. Second, advanced civilizations lose interest in creating ancestor simulations. Or third, the spine-chilling option: we're almost certainly living in one. The logic is simple. If any civilization ever reaches the capability to simulate conscious beings, they'd likely create countless simulations, far outnumbering the one real universe. Statistically, the odds tilt heavily toward us being artificial minds in someone else's machine. But how would such a simulation even work? Think of the universe as a pixelated grid at the smallest scales. Planck length, the tiniest measurable unit of space, could be the resolution limit of our cosmic rendering engine. Quantum indeterminacy, the way particles exist in probability waves until observed, might be the universe's way of optimizing processing power, only calculating details when absolutely necessary. Even the speed of light could be a hard-coded limit to prevent system overload, like a cosmic frame rate cap. The implications ripple through every aspect of existence. If we're in a simulation, does free will exist, or are our choices predetermined by underlying code? Are glitches in the matrix, like déjà vu or quantum entanglement, actual bugs in the system? Some scientists search for proof in high-energy physics experiments, hunting for telltale pixelation in particle collisions or anomalies in cosmic ray distributions that might reveal the simulation's underlying architecture. Yet the hypothesis also opens dizzying possibilities. If reality is programmable, could we one day hack it? Could simulated beings eventually become simulators themselves, spawning nested universes like digital Russian dolls? And if this is all a construct, what lies outside it? An alien server farm, a post-human civilization, or something beyond comprehension? Whether you find the idea terrifying or exhilarating, it forces us to confront fundamental questions. If we're living in someone else's simulation, does that make our experiences less meaningful? Or does it deepen the wonder, knowing that even as potential lines of code, we're part of a cosmos vast enough to question its own existence? The simulation hypothesis may never be proven, but like all great thought experiments, its value lies in how it reshapes our perspective, making the familiar seem suddenly, thrillingly strange. Quantum entanglement might be the universe's most baffling handshake, a phenomenon so strange even Einstein struggled to accept it. Picture two particles born from the same quantum event, their properties locked in perfect sync no matter how far apart they drift. Change the spin of one and the other instantly flips to match, as if space and time between them don't exist. Einstein famously dismissed this as spooky action at a distance, convinced it violated relativity's cosmic speed limit. Yet decades of experiments, from photon pairs split across labs to satellites beaming entangled particles across continents, have proven this eerie connection is real. But here's the twist. What if this quantum weirdness isn't confined to tiny particles? What if the entire cosmos is stitched together by entanglement on a scale we're only beginning to fathom? Take black holes, for instance. When matter falls into a black hole, conventional physics says it's lost forever. But quantum mechanics insists information can't vanish, it has to go somewhere. The solution: entanglement. Theorists suggest that particles inside a black hole might remain quantum linked to radiation leaking out, a cosmic lifeline preserving information across the event horizon. This idea, known as the ER equals EPR conjecture, proposes that entanglement and wormholes, those hypothetical space-time shortcuts, might be two sides of the same coin. In other words, particles entangled across the universe could be connected by invisible bridges in space-time, a hidden architecture weaving reality together. Then there's the cosmic web. Just as entangled particles influence each other instantly, could galaxies or even galaxy clusters share a similar bond? Some models suggest the universe's large-scale structure. Those vast filaments and voids might emerge from quantum entanglement operating in the early cosmos. Imagine the Big Bang as a quantum event, its initial conditions entangled on a cosmic scale. As the universe expanded, those quantum links stretched, imprinting their patterns on the distribution of matter. If true, the cosmic web isn't just shaped by gravity, it's a fossilized quantum network, its threads echoing connections forged in the first moments of time. The implications are staggering. If entanglement operates beyond the quantum realm, it could rewrite our understanding of space itself. Instead of a passive backdrop, space-time might be a dynamic tapestry, its geometry shaped by quantum connections. This could explain why the universe appears so finely tuned for life, because its fundamental structure is woven from relationships, not just particles. Experiments are already pushing entanglement to new extremes, testing whether it can survive in Earth's orbit or across astronomical distances. Future telescopes might even search for entanglement's fingerprints in the cosmic microwave background, hunting for anomalies that betray a universe far more interconnected than we ever imagined. Yet for all its promise, entanglement remains a paradox. How can particles communicate faster than light without breaking relativity? Is the universe fundamentally non-local, with everything secretly linked? Or are we glimpsing a deeper layer of reality, where space and time emerge from something more primal? Whatever the answer, one thing's certain: the spookiness Einstein resisted might be the very glue holding the cosmos together, a hidden symphony of connections playing just beneath the surface of the visible world. White holes are the universe's ultimate cosmic rebels where black holes devour. White holes might erupt. Imagine a celestial fire hose blasting matter and energy outward at impossible speeds, defying gravity's pull with a force so violent, nothing can enter, only escape. These hypothetical objects are the yin to black hole's yang, a mathematical flip of Einstein's equations where time itself runs backward. While no white hole has ever been observed, their theoretical existence could rewrite some of the cosmos' most dramatic events, even offering a wild new origin story for reality itself. Think of a white hole as a black hole in reverse. Instead of an event horizon sucking everything in, it's a boundary hurling everything out. Matter, light, space-time all expelled in a torrent too fierce for anything to cross back over. Some physicists speculate that gamma-ray bursts, the most energetic explosion since the Big Bang, could be white holes flickering to life for fleeting instants. Others go further, suggesting the Big Bang itself might have been a primordial white hole, the ultimate cosmic reset button where an entire universe burst into being from an unfathomable singularity. The math behind white holes is just as mind-bending as their implications. General relativity allows for their existence, but with a catch: they'd require conditions so exotic they border on fantasy. Matter would need to emerge from a singularity already in place, like a magician pulling an endless scarf from a hat that was never filled. Quantum gravity theories offer a tantalizing workaround. What if white holes aren't separate objects at all, but black holes viewed from the other side of time? In this scenario, a black hole's crushing collapse in our universe could birth a white hole in another, spewing matter into a parallel cosmos like a cosmic relay race handing off the baton of existence. Yet for all their theoretical allure, white holes face one glaring problem: nature seems to hate them. The second law of thermodynamics insists the universe tends toward disorder, making a process that reverses entropy seem as likely as a shattered glass reassembling itself. But here's the twist: if white holes are somehow locked behind black holes, existing in regions of space-time cut off from our own, they might evade these cosmic rules entirely. It's a loophole that keeps them alive in equations, if not yet in telescopes. The search for evidence is as creative as the theories themselves. Some models predict white holes would leave behind ghost radiation, an echo of their explosive birth lingering in the cosmic microwave background. Others suggest that fast radio bursts, those mysterious, milliseconds-long blasts of energy from deep space, could be white holes coughing up remnants of long-vanished universes. Even if they remain forever out of reach, white holes challenge us to rethink the most basic assumptions about cause and effect, time's arrow, and the very nature of existence. Because if space-time can bend so far that a hole becomes its own opposite, what other impossibilities might be waiting in the equations? Perhaps the most profound idea white holes offer isn't about their physics, but their poetry. In a universe where so much ends in collapse and silence, they whisper a tantalizing alternative: that endings might also be beginnings, that destruction could birth creation, and that somewhere beyond the edge of a black hole's darkness, there's a flash of light waiting to rewrite the story. The Big Bang might not have been the beginning, just the latest chapter in an endless cosmic saga. Imagine a universe that breathes, expanding and contracting like a colossal lung, where each collapse births a new explosion, a fresh cosmos rising from the ashes of the old. This is the Big Bounce, a radical reimagining of reality where the Big Bang wasn't a singular event, but one tick of an infinite cosmic metronome. At the heart of this idea lies a simple yet profound twist. Instead of collapsing into a crushing singularity, the universe rebounds. Picture a rubber band stretched to its limit. Just as it's about to snap, it recoils with newfound energy. In the Big Bounce scenario, dark energy, that mysterious force accelerating the universe's expansion, might actually be the key to the rebound. As galaxies drift apart and space grows colder, dark energy could eventually reverse its role, pulling everything back together in a cosmic reset. The result: no fiery oblivion, no infinite density, just a smooth transition into the next cycle. What's fascinating is how this model sidesteps the gnarly problem of singularities. In traditional Big Bang cosmology, all the universe's matter and energy were once crammed into an infinitely dense point where physics breaks down. But in a bouncing universe, there's no true singularity, just a moment of maximum compression before the rebound, like a ball bouncing off the ground without flattening into nothingness. Some theories even suggest quantum gravity effects could prevent total collapse, acting like a cosmic trampoline that cushions the fall and propels the universe into its next phase. The implications are staggering. If the Big Bounce is real, our universe isn't just one isolated experiment. It's part of an endless sequence, each cycle inheriting traces of the last. Tiny quantum fluctuations from a previous bounce might have seeded the galaxies we see today, like echoes of a forgotten era. And dark energy, instead of tearing the cosmos apart, it could be the universe's way of preparing for its next act, like a coiled spring storing energy for release. But how would we ever know? Clues might lurk in the cosmic microwave background, the afterglow of the Big Bang. If space-time bears scars from a prior contraction, subtle twists in the polarization of ancient light or anomalies in the distribution of galaxies, future telescopes could spot them. Some physicists even hunt for hypothetical relic particles left over from a pre-bounce universe, cosmic fossils hiding in plain sight. Yet the Big Bounce isn't just about physics, it's about perspective. If the universe cycles endlessly, then every ending is also a beginning. Stars, planets, even life itself might rise again in some form, an infinite tapestry of possibility. It's a vision both humbling and hopeful, that no matter how far the cosmos expands or how cold it grows, the story isn't over, just paused, waiting for the next bounce. Primordial black holes could be the universe's oldest relics, tiny, dense remnants from the very first second after the Big Bang, hiding in plain sight. While most black holes form from collapsing stars, these ancient anomalies might have been forged in the furnace of the early cosmos, when extreme pressures and temperatures squeezed matter into microscopic points of infinite density. Picture a black hole no larger than an atom, yet as massive as a mountain, drifting silently through space for billions of years. If they exist, they could be the missing piece to some of astronomy's greatest puzzles, from the nature of dark matter to how galaxies assembled so quickly after the birth of the universe. What makes primordial black holes so intriguing is their sheer range of possibilities. Some could be as light as a pebble, evaporating almost instantly due to Hawking radiation. Others might weigh as much as a planet, lurking undetected in the dark corners of our galaxy. And if they cluster in halos around galaxies, they could explain why dark matter's gravitational pull is so strong yet so invisible. Unlike exotic particles, which remain theoretical, these black holes would be tangible, just fiendishly hard to spot. Imagine the irony. The darkest objects in existence might be the dark matter we've been searching for all along. But their influence could go even deeper. In the chaotic early universe, primordial black holes might have acted as cosmic seeds, their immense gravity pulling in gas and dust to form the first proto-galaxies. Simulations show that even a sparse population of these objects could have jump-started structure formation, solving the mystery of how galaxies grew so large so fast. It's like dropping stones into a still pond. The ripples they create could have set the entire cosmic web into motion. So how do we find them? One clue lies in microlensing. When a black hole passes in front of a distant star, its gravity bends the star's light, causing a brief but detectable brightening. Projects like the Subaru telescope's Hyper-Subprime Cam are scanning millions of stars for these telltale flickers. Another approach listens for the final bursts of energy as tiny black holes evaporate, their depths potentially releasing gamma-ray flashes that telescopes could catch. And then there's the wild card. If two primordial black holes collided, they'd send gravitational waves rippling through space, a signal observatories like LIGO might one day detect. The hunt is high stakes. If primordial black holes are real, they'd rewrite cosmic history, proving that the universe's architecture was shaped not just by particles and forces, but by lurking gravitational traps from the dawn of time. They'd blur the line between the quantum and the cosmic, between the visible and the unseen. And most tantalizing of all, they might still be out there, silent and ancient, waiting to reveal the universe's best-kept secrets. The cosmic microwave background should be a random tapestry, a quiet echo of the Big Bang's aftermath, evenly distributed in all directions. But when scientists mapped its faintest whispers, they stumbled on something unsettling, a pattern that defies expectations. Dubbed the axis of evil, this eerie alignment shows temperature fluctuations in the CMB that aren't just uneven, they're suspiciously coordinated, as if the universe itself has a hidden north and south pole. The name might sound dramatic, but the implications are profound. If the cosmos has a preferred direction, It challenges one of cosmology's bedrock principles that the universe is fundamentally the same everywhere, no matter where or how you look. Digging deeper, the anomaly reveals even stranger quirks. The CMB's fluctuations appear slightly cooler in one hemisphere and warmer in the other, with an axis that oddly aligns with our solar system's plane. At first, scientists dismissed it as a fluke, a cosmic coincidence, but as data piled up from Planck and WMAP satellites, the signal refused to vanish. The odds of this happening by chance, less than 1 in 1,000. Suddenly, the question wasn't whether the anomaly existed, but whether it was a crack in our understanding of reality itself. One radical explanation suggests the axis of evil might be a fossil, a scar from something that happened before the Big Bang. Could our universe have collided with another, leaving a gravitational imprint on the CMB? Or is this the shadow of a parent universe, a remnant from a cycle of cosmic rebirth? Some theories even propose that space-time isn't uniform, but subtly warped on scales so vast, they twist the entire observable cosmos like a slow spinning top. Then there's the unsettling possibility that we're seeing the handiwork of an unseen force. Modified gravity, exotic dark energy with directional properties, or even quantum entanglement operating on cosmic scales could, in theory, leave such a mark. But here's the catch. No current model cleanly explains the axis of evil without unraveling other well-tested physics. It's as if the universe handed us a jigsaw piece from a puzzle we didn't know existed. For now, the anomaly remains a tantalizing enigma, an open question scribbled in the margins of cosmology's textbook. Future telescopes, like the Simons Observatory, aim to scrutinize the CMB with unprecedented precision, hunting for clues that might confirm or dissolve the mystery. But whether it's a statistical ghost or a gateway to new physics, one thing's certain: the axis of evil reminds us that the universe still holds cards it hasn't shown. And somewhere in that faint afterglow, there might be whispers of a reality far stranger than we've dared to imagine. Wormholes aren't just science fiction, they're cosmic tunnels carved into the very fabric of space-time, predicted by Einstein's equations over a century ago. Picture folding a piece of paper so two distant points touch, then piercing through with a pencil. That's the essence of a wormhole, a shortcut through the universe's crumpled geometry, where a journey that should take billions of years could become a stroll across an invisible bridge. But here's the catch: these tunnels are fantastically unstable. Without something to prop them open, they'd snap shut faster than a blink, crushing anything inside. That's where exotic matter comes in, a hypothetical substance with negative energy, repelling gravity's pull like an anti-glue to keep the wormhole's throat gaping wide. The allure of wormholes isn't just about speed. They're portals to possibilities. A wormhole might not just connect two places in our universe, it could stitch realities together, linking parallel dimensions or alternate timelines. Some theories even suggest that entangled particles, those spooky quantum twins, might be tied together by microscopic wormholes, their instant connection a hint of spacetime's hidden plumbing. It's a dizzying thought. The universe might be riddled with these unseen passageways, like termite tunnels in the woodwork of reality. But could we ever use one? The challenges are staggering. First, you'd need to find a naturally occurring wormhole if they exist at all. Then there's the problem of cosmic roadblocks. Quantum effects near a wormhole's entrance might turn it into a lethal blender of radiation, shredding matter into its fundamental particles. And even if you survived the trip, there's no guarantee you'd arrive in one piece or in the same era you left. Wormholes could warp time as easily as space, making them potential time machines. Step in on Monday, emerge 1,000 years earlier with no way back. Yet for all their hurdles, wormholes captivate scientists and storytellers alike. Advanced civilizations, if they're out there, might have cracked the code, stabilizing wormholes with technology beyond our grasp. Some researchers even speculate that pulsars, those spinning neutron stars emitting rhythmic radio waves, could be natural wormhole markers, their precise flashes acting as navigational beacons for travelers. Others propose that dark energy, the mysterious force accelerating the universe's expansion, might hold the key to keeping wormholes open, its repulsive gravity counteracting collapse. The deeper we dig into the math, the stranger it gets. Wormholes might not just be tunnels, they could be bubbles of spacetime pinched off from our own, floating in a higher dimensional bulk. Imagine a soap film with bubbles clinging to its surface. Our universe might be just one film in a cosmic foam, with wormholes threading between them. This isn't just fantasy, it's grounded in serious physics, like the holographic principle and string theory's hidden dimensions. Whether wormholes are real or just elegant equations, they force us to rethink the limits of space, time, and exploration. They're a reminder that the universe might be far more connected, far more porous than it appears, and if we ever uncover one or build one, it wouldn't just revolutionize travel. It would redefine our place in the cosmos, turning distant stars into neighbors and weaving the fabric of reality into something richer, stranger, and more wondrous than we ever imagined. Supersymmetry whispers of a universe far more elegant than the one we see, a hidden mirror world where every particle we know has a secret twin. Imagine an invisible dance unfolding beneath reality's surface, where electrons, quarks, and photons are paired with mysterious counterparts, selectrons, squarks, photons. These sparticles, as physicists call them, would be heavier, fleeting, and utterly alien, yet their existence could solve some of science's deepest mysteries. At its heart, supersymmetry isn't just about new particles, it's about balance. It suggests that the chaotic zoo of fundamental forces and particles we've discovered is really two sides of the same cosmic coin, linked by a symmetry so profound, it reshapes our understanding of everything. What makes this idea so compelling is how neatly it patches the holes in our current physics. Take the Higgs boson, for example. Its mass is suspiciously low compared to what quantum theory predicts, as if some invisible hand is canceling out extreme values behind the scenes. Supersymmetry's particles could be that hand, their interactions delicately tuning the Higgs to the precise weight we observe. Then there's dark matter. If the lightest superpartner is stable, as some models suggest, it could be the elusive particle that makes up 27% of the universe, silently shaping galaxies while evading detection. It's a tantalizing two-for-one, solve the Higgs puzzle and unmask dark matter in a single stroke. Yet for all its elegance, supersymmetry remains frustratingly out of reach. The Large Hadron Collider, designed in part to hunt for sparticles, has yet to find a trace. Each new energy level, each more powerful collision, has returned empty-handed, or at least without the clear signatures theorists hoped for. Some versions of the theory have already been ruled out, forcing physicists to tweak their models, pushing predicted sparticle masses higher into energy realms we can't yet probe. Critics argue this flexibility makes supersymmetry untestable, a theory that constantly retreats to the next unobserved horizon. But here's the twist: absence of evidence isn't evidence of absence. Supersymmetry might simply be hiding in plain sight, its particles too heavy or too weakly interacting for current tools to spot. Future colliders, like the proposed Future Circular Collider with its 50-mile tunnel, could blast protons together at energies 10 times higher than the LHC, peeling back layers of reality we've never seen. Or perhaps sparticles reveal themselves indirectly, through subtle anomalies in rare particle decays or the cosmic microwave background's faintest glimmers. Beyond the hunt for particles, supersymmetry offers something even grander, a bridge between quantum mechanics and gravity. In this framework, the frenetic quantum world and the smooth curvature of space-time aren't opposing forces, they're facets of a deeper unity. String theory, for instance, relies on supersymmetry to weave its extra dimensions into a coherent whole. If confirmed, it wouldn't just fill gaps in the standard model. It would rewrite our cosmic origin story, revealing a universe built on harmonies we're only beginning to imagine. So while supersymmetry remains unproven, it's far from abandoned. Like a compass pointing toward uncharted territory, it guides physicists through the wilderness beyond known physics. Whether it's confirmed or ultimately set aside, the quest for supersymmetry has already expanded our vision of what's possible. And in that search, we might stumble upon truths even more extraordinary than the symmetry we first sought. Black holes aren't just cosmic vacuum cleaners, they're shredders of reality itself, tearing apart not just matter but the very information that defines it. Here's the nightmare scenario. Toss a book into a black hole, and according to Einstein's general relativity, it's gone forever, crushed into the singularity's infinite density. But quantum mechanics insists that information, the arrangement of particles, the story written on those pages, can never truly vanish. It might get scrambled, diffused, or hidden, but it must persist. This clash isn't just academic, it's a battle for the soul of physics, forcing us to ask, does the universe forget? Stephen Hawking first spotlighted this paradox when he realized black holes emit radiation, slowly evaporating over eons. If a black hole vanishes, what happens to the information it swallowed? Hawking initially thought it was erased, a conclusion that horrified quantum theorists. The math was clear. Information loss would mean the universe is fundamentally unpredictable, like a movie reel burning frame by frame. But in the 1990s, Hawking changed his mind, conceding that information might escape, encoded in the radiation itself. Imagine burning that book and claiming its ashes still hold the text if only you could decode them. That's the promise of Hawking radiation. A cosmic cipher preserving data in seemingly random particles. Yet the devil's in the details. For information to escape, it would need to be imprinted on the radiation with near infinite precision, a process so delicate it strains the limits of quantum theory. Some physicists propose holography as a work around the idea that all the information inside a black hole is actually smeared across its event horizon, like a 3D image projected onto a 2D surface. In this view, the book isn't destroyed, it's pulped into a quantum PDF stored on the black hole's surface, with Hawking radiation serving as the slow, garbled printout. But skeptics aren't convinced. If information escapes, where's the proof? The radiation we've detected from black holes is too faint to test these ideas directly, leaving theorists to wrestle with equations and thought experiments. One radical solution suggests black holes don't evaporate completely, but leave behind microscopic remnants, information-packed fossils too small to detect. Others argue the paradox hints at something deeper, that spacetime itself is an emergent property, and black holes are glitches in its code, revealing a more fundamental layer of reality where information flows freely. The stakes couldn't be higher. If black holes can destroy information, it means our universe has a built-in delete button, undermining the determinism that underpins modern physics. But if they preserve it, even in some scrambled form, we might be staring at the key to unifying quantum mechanics and gravity. Every photon of Hawking radiation, every simulation of evaporating black holes, brings us closer to an answer. And when we find it, we won't just solve a paradox, we'll uncover the universe's deepest operating manual, written in the ashes of its most enigmatic objects. The universe's greatest architects don't glitter in telescopes or blaze across the night sky. They work in the shadows, shaping existence from behind the scenes. Dark matter weaves its invisible threads between galaxies. Black holes sculpt space-time with their gravitational chisels, and even the vacuum of space itself crackles with quantum potential, birthing particles from nothingness. These unseen forces are the true builders of reality, their blueprints written in equations we're still learning to read. Consider this: every time we map the cosmos, we're only seeing half the picture. The galaxies we admire are like streetlights along a highway. What really matters is the road itself, the dark matter scaffolding holding everything together. Without it, stars would scatter like marbles dropped on a tilting table, and the cosmic web would unravel into chaos. Yet for all its power, dark matter remains a ghost, revealing itself only through the gravitational fingerprints it leaves behind. It's as if the universe is a puppet show, and we're only now noticing the strings. Black holes play an equally mysterious role. They're not just destructive voids, they're cosmic sculptors. Their immense gravity bending light like a prism, and their collisions sending ripples through space-time itself. When two black holes merge, they don't just vanish. They create gravitational waves that echo across the universe, a reminder that even the darkest objects leave traces. And let's not forget their most mind-bending feature, event horizons, the ultimate one-way streets where time itself slows to a crawl. These phenomena aren't anomalies, they're clues, hinting at a deeper layer of physics where space and time intertwine in ways we're only beginning to grasp. Then there's the quantum realm, where particles pop in and out of existence like bubbles in a cosmic foam. At this scale, the universe isn't solid and predictable, it's probabilistic, flickering between possibilities until observed. Some theories suggest these quantum fluctuations might be the seeds of cosmic structure, microscopic wrinkles stretched into galaxies by inflation's exponential growth. If true, it means the largest structures in existence owe their origins to the tiniest vibrations of reality. What's thrilling is how much we still don't know. Every discovery peels back another layer, revealing new questions. Could dark matter be part of a hidden sector of particles governed by forces we've yet to discover? Are black holes gateways to other universes, or the engines of cosmic recycling? And what if the quantum foam isn't just background noise, but the canvas on which space-time is painted? The beauty of these mysteries isn't just in solving them, it's in the journey of exploration. Each answer rewrites our understanding of reality, connecting the infinitesimal to the infinite. And as we stand on the edge of the unknown, one thing becomes clear: the universe isn't just stranger than we imagine. It's stranger than we can imagine. The next great revelation won't come from looking harder at what we see, but from daring to search where we've never thought.